Hello, scholars. So today we're going to take a look at Chapter 2, Big Concept Number 4, Real Zeros of Polynomial Functions. So our learning targets today, I am learning to find zeros of polynomial functions. I'm learning to find complex zeros of polynomial functions. This is a huge section, and when I mean huge, I mean it's ginormous. So I decided to split it over 2 videos. So today we're actually going to just focus on this first learning target. I am learning to find zeros of polynomial functions. So when we take a look, we're going to recall that a polynomial function of degree n has at most n real zeros, where the real zeros are either rational or irrational. And this is where we come to the rational zero theorem. It says if a polynomial of the form f of x equals all of this mumbo jumbo with degree greater than 1, the integer coefficients, and a sub 0 can equal 0, then every rational zero of f has the form p over q. Now this is important. P and Q have no common factors other than plus or minus 1. P is your constant. This is your P. Q is your leading coefficient. This is your Q. So in essence, you're going to find all your factors of P and all your factors of Q. And then when you divide P over Q, you will find your possible real zeros. Your rational real zeros, at least. So once you know all the possible real zeros of a polynomial function, you can use that direct or synthetic substitution. Knowing y'all, you want to use that synthetic substitution. It saves you a lot of time and a lot of heartache. So we're going to actually look at this first example, and we're going to start off pretty easy. It says, list all possible rational zeros of each function, then determine which, if any, are zeros. So we need to first determine what our P is and what our Q is. Remember, P is that constant value. It is that term that does not have a variable. So P in this case is 1. So I'm going to come over here and I'm going to put, 1. P is 1. Now, Q is the leading coefficient. So I go to my highest exponent and I see what is the number in front. Well, I don't see 1, which means that it is also a 1. So now I have to list all the factors of P, which in this case are plus or minus 1, and all the factors of Q, which are plus or minus Q. So now let's take a look. What is P over Q? Equals plus or minus 1 over plus or minus 1, which is either positive 1 or negative 1. So that gives us 2 possible real zeros. Now, using that synthetic substitution, that synthetic division, we're going to first determine if 1 or negative 1 is a possible zero. So remember, from our last section, all we do is substitute that value in, that C value. So let's check that positive 1 first. F of 1 is 1 cubed plus 2 times 1 plus 1, which is 1 plus 2 plus 1, which is 4. 4 does not equal 0. So 1 is not a 0. Now let's check f of negative 1. So we get negative 1 cubed plus 2 times negative 1 plus 1. So we get negative 1 minus 2 plus 1. We get negative 2. Once again, not equal to 0. So negative 1 is not a 0. So in both these cases, we did not have any real zeros. So there are no real zeros for this example. All right, so now we're going to take a look at the next example. We're going to take a look at our P's and our Q's. So in this case, our P is that negative 9. So P equals negative 9. So factors of P are plus or minus 1, plus or minus 3, plus or minus 9. Q equals 1 because there's a leading coefficient of 1, which means we have factor of 1. So now when we look at our P's over Q's, we get plus or minus 1 over 1, plus or minus 3 over 1, and plus or minus 9 over 1. So now we have 6 possible zero values. we're going to have to substitute in all of these p over q's to determine if the values can or equal 0 and provide a real 0. So we'll do f of 1 equals, all right, so f of 1, we have 1 to the 4th plus 4 times 1 cubed minus 12 times 1 minus 9. So that's 1 plus 4 minus 12 minus 9 equals what? Negative 17. All right, so we have to do that for every single one of these p's over q's. That's 6 different values we have to check. So we know that this one doesn't work. However, we're going to save us some time. So we have f of negative 1 next. So I'm going to go over here. I'm going to go to Desmos, which I already have popped up, and I've already entered in our expression. I need to check if negative 1 is a value. So I'm going to click on my expression. I'm going to go to the table, and notice it says convert to table. And now when I look, negative 1 yields a result of 0. So I'm going to go back over here, and instead of doing all that work, I know that negative 1 gives me 0. So now I need to find out what about positive 3. All right, so I'm going to go back to my Desmos calculator, and I'm going to type in positive 3. That gets me 144. 144 isn't what I'm looking for, but I'm going to write it down. Now we'll go to f of negative 3. And so we go back to our Desmos. We go negative 3. Negative 3 does yield a 0. So now we have 0 here. Now we need to do f of 9 and f of negative 9. So when I go back to my Desmos, I have 9, and negative 9. Ouch, both of those are high numbers, not giving us that 0. So 9, it was 9360, and negative 9 yielded 3744. So we have 2 possible zeros, f of negative 1 and f of negative 3. We're going to use our synthetic division now to check. To simplify this out, so we have negative 1. We use our leading coefficients, 1, 4, 0, negative 12, negative 9. Who recalls why we put a 0 in? Well, if you said because we needed that placeholder for the x squared, you'd be absolutely correct. So using that synthetic division, I'm going to drop this 1 down. Negative 1 times 1 is negative 1. 4 plus negative 1 is 3. Negative 1 times 3 is negative 3. 0 plus negative 3 is negative 3. Negative 1 times negative 3 is a positive 3. Negative 12 plus 3 is negative 9. Gets us that positive 9 and 0. So now we know that it's x plus 1 times x cubed plus 3x squared minus 3x minus 9. I'm going to use that synthetic division again, but this time with my already factored expression of x cubed plus 3x squared minus 3x minus 9, and this time we're going to use it with that negative 3 value. So I have negative 3, and then I have a leading coefficient of 1, 3, negative 3, negative 9, and I'm going to follow that synthetic division once more. I drop the 1. Negative 3 times 1 is negative 3. 3 plus negative 3 is 0. Negative 3 times 0 is 0. Negative 3. Just keep going through the motions. And yes, in fact, now we have that this becomes x plus 1, x plus 3, x squared minus 3. All right, so now what are my possible real zeros? Your real zeros are x equals negative 1, x equals negative 3, and those were the easy ones because we literally just checked those. But now we have to take this expression and set it equal to 0. So my next 2 real zeros are plus and minus the square root of 3. So we have 4 real zeros, which coincides with the fact that our highest exponent is that 4, which says, hey, at most you can have 4 solutions. All right, let's go down to our next example. We're going to do this again. So now let's figure out what our P is and what our Q is. So here we have P equals 8, positive 8. So we have plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. All right, and then we have our Q, which in this case is 3, because it is that leading coefficient. So 3, which means we have plus or minus 1 and plus or minus 3. So now what are our P's over Q's? Well, 1 over 1, 2 over 1, 4 over 1, and 8 over 1. So that took care of all of the P's over our first Q, and now we have to do all of our P's over our second Q. So that gets us plus or minus 1/3, plus or minus 2/3, plus or minus 4/3, and plus or minus 8/3. Wow, so taking a look, we have 1, 2, 3, 4, 5, 6, 7, 8, 16 possible zeros. However, we know that at most only 3 are going to work. So now we're going to go back and we're going to substitute each one of these P's and Q's in to my H. So let's start off with a positive 1. So H of positive 1 equals, now let's take a moment there, let's breathe. Let's go to our Desmos calculator, enter in this function, and use our table feature. So here we have our Desmos calculator. We're going to click on the function, hit the little gear. It'll give us the table option, and now we have a table. So the first value we're going to check is positive 1. That gives us a negative 18. The next value we're going to check is negative 1, which gets us 20. And then we'll go to 2, which gets us negative 40. And then negative 2 gets us 0. All right, so now if we take a look, negative 2 was my first real zero. So let's go back to our OneNote and list our possible values. So we know that H of 1 was negative 18. H of negative 1 equals 20. H of 2 was negative 40. But then when we got to H of negative 2, we got to 0. Now, this is a cube, which means after we do synthetic division one time, it will yield us a leading coefficient term that has a square, which we know is much more factorable. So let's go ahead and do that synthetic substitution right now. Let's start with that synthetic division. We have 3, negative 7, negative 22, positive 8. All right, so now we drop our 3, we go through the motions. All right, so we now know that this factors out to x plus 2, 3x squared minus 13x plus 4. This is a trinomial, but in fact it is a quadratic trinomial, which means we can factor this. We don't have to do synthetic substitution anymore. We don't have to find any more of our P's and Q's. We can simply factor from here. So we're going to build that bridge. 3 times 4 is 12. Factors of 12, that get me 13, or 1 and 12. So now this x plus 2 comes down. But now I have 3x squared minus 12x minus 1x plus 4. And remember, this is where we're going to do that factor by grouping. So what is our greatest common factor of 3x squared minus 12x? Well, if you said it was 3x, you'd be absolutely correct, and then I'd be left with x minus 4. All right, well, I know that our second binomial term has to be x minus 4. Right now I have negative x plus 4, so that greatest common factor is actually that negative 1. So when I pull this all down, I have x plus 2, 3x minus 1, x minus 4. So we know that this gives us x equals -2. This one gives us x equals 1/3. And this one gives us x equals 4. There are our 3 zeros, which means our real zeros are as follows. X equals -2, x equals 1/3, and x equals 4. Now taking a look, that is 3 zeros. We knew we were going to have at most 3 zeros, and that was far easier than going through all of that hassle of substituting our p's over q's into our function. All right, so that option, that last example, had a possible of 16 p's over q's that potentially we were going to have to substitute in. That's a lot of freaking work, guys. We don't want to do that. That's too much. That is too much. So we're actually going to talk about the upper and lower bounds test. And that's one way to narrow that search of real zeros. So we can cut some of that extra work out. We're all about taking those shortcuts. So we have the upper and lower bounds test. That says when you enter your polynomial and you graph it, you're going to just take a look at the graph and you're going to see where your graph crosses the x-axis. When that happens, you'll be able to narrow down considerably the number of x's we have to test, those p's over q's. So for the upper and lower bounds test, follow these steps. 1, graph the function to determine an interval in which the zero lies. Then go through all the steps that we did beforehand, the synthetic substitution, using those upper and lower bound intervals, and then the rational zero theorem to find all the rational zeros, or real zeros. So now we're going to determine an interval in which all the real zeros of h of x equals 2x to the 4th minus 11x cubed plus 2x squared minus 44x minus 24 exist. So, like I said, first, step 1, graph all of the real zeros. So I'm going to go to our Desmos calculator. I've entered in the function and take a look. It is already graphed here to the right. If I look at this x-axis, I know that here's my -1, and this is, I don't know what that is specifically. So my range is going to be between -1, because it looks like it's crossing around -1, or before -1, and 7. So I'm only going to look at the p's and q's between -1 and +7, because that gives us that little wiggle room, but cuts down the number of values that we're going to have to test. So first things first, let's look at our interval, which we said was between -1 and 7. So those are the values that we're going to test, and I did put the brackets around them because I am going to test those specific values. So now, what is my p? My p is -24. So factors of -24 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 24. And then we have q. Q is 2. It says plus or minus 1, plus or minus 2. So when we take a look at that, that's 1, 2, 3, 4, 5, 6, 7, 8 p's over 2 q's. That's potentially, there's 16 here. When we move our duplicates, we end up with a couple more. That's 18 possible p's over q's that we would have to test. However, if we only look at our p's divided by q's that are between -1 and 7, we'll be able to get rid of a lot. So we have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 24. That was all of our p's over our first q. And now all of our p's over our second q give us plus or minus 1/2. And then we have 2 over 2, which is 1, plus or minus 3/2, and then plus or minus 4 over 2, which is 2, 6 over 2, which is 3, 8 over 2, which is 4, 12 over 2, which is 6, and 12 over 2, which is 12. All right, but we know we only need values between -1 and -7, which are +7, which means I can get rid of -2, -3, -4, negative 6, negative 8, negative 12, and negative 24, because those are all smaller than our lowest boundary of negative 1. All right, and taking a look here, this is negative 1.5, so I can get rid of the negative 3/2. All right, so now we can get rid of all values bigger than 7. So this gets rid of the plus 8, the plus 12, and the plus 24. So we just went from 18 different values to 1, 2, 3, 4, 5, 6, 7, 8. So less than half of the values we have to test. So now we're going to go back to our handy dandy Desmos calculator, and we're going to just cycle through these P's over Q's. So let's h of 1, h of negative 1, then h of 2, h of 3, h of 4, h of 6, h of 1/2, h of negative 1/2, and then h of 3/2. All right, so we're going to go to our handy dandy Desmos calculator, which I've already done to save a little time on this video, but I've showed you how to do it 2 or 3 times now, so you should be able to do it on your own. So h of 1 gets us that negative 75, h of negative 1 is positive 35, h of 2 is negative 160, h of 3 is negative 273, h of 4 is negative 360, h of 6 is 0, so we can put a little box around here saying, okay, we're going to make sure to use this value. H of 1/2 is negative 46.75. H of negative 1/2 is 0, so there's our second 0 that we can use. And then h of 3/2 is 93.75. All right, so we're going to go through that synthetic substitution and, simplify this factoring down a bit. So let's start with 6. So we'll go to 6. We know our leading coefficients were 2, negative 11, 2, negative 44, and negative 24. And so we'll go through that synthetic division process. And the 6 does work because, we did that synthetic substitution, and we're left with 2x cubed plus x squared plus 8x plus 4. But now we're going to use that negative 1/2 and go through that synthetic division again with our new leading coefficients of 2, 1, 8, and 4. And so when we go through this process, we end up getting, let's go back over here, we have x minus 6, x plus 1/2, then x squared plus, not x squared, 2x squared, silly me, 2x squared plus 8. However, notice, what do we have right here? A GCF. Let's go ahead and pull that out. The GCF was 2, so I'm just going to put that 2 right in front. X minus 6, x plus 1/2, x squared plus 4. So here we get real zeros of 6, or x equals 6, and x equals negative 1/2. What happens here with the x squared plus 4? Well, if we put that equal to 0, x squared plus 4 equals 0, we get x squared equals negative 4. So x equals plus or minus 2i. And we know i's are imaginary numbers, so it's not considered a real zero. Our only real zeros are 6 and negative 1/2. All right, let's go on to what we call Descartes' rule. And I really like Descartes' rule because it helps save us work later down the road. We're just going to touch on it a little lightly in this video. That way we can really hit it hard in our next video. So Descartes' rule gives us information about the number of positive and negative real zeros. So this is another way we can actually limit the numbers of p's and q's, or p over q's, that we're substituting into our polynomial function to determine the real zeros. So here we have our polynomial function with our real coefficients. It says the number of positive real zeros of f is equal to the number of variations in the signs or less that number by some even number. So less an even number. And then the negative real zeros is if when we substitute negative x into our function, we have the number of variations less than an even number. So what in the world does that even mean? Well, let's first take a look at this function g of x. So we have g of x equals negative 3x cubed plus 2x squared minus x minus 1. All right, so this is that positive x value. So right here we have that positive x. So right now we're going to determine how many positive real zeros are possible. And all we have to do is look at our sign changes first. So we have a negative 3 to a positive 2. So that is a sign change. We have a positive 2 to a negative x. Sign change. Then we have a negative x to a negative 1. That's not a sign change. So we had 2 sign changes. So that means we have 2 or 0 because that means less an even number. So 2 minus 2 is 0. So we have 2 or 0 positive real zeros. All right, so let's take a look at our negative zeros. So we substitute in that negative x. So negative 3 times negative x cubed plus 2 times negative x squared minus negative x minus 1. This one has to do a little bit more substitution and simplification because we have these negative x's. So we know negative x cubed still yields a negative x cubed. So negative 3 times negative x is now positive 3x cubed. Negative x squared turns into a positive x squared. So that's positive 2x squared plus x, because a negative times a negative, minus 1. So let's take a look. How many sign changes? Positive to positive, no sign change. Positive to positive, no sign change. Positive to negative. Boom, 1. So that means we have 1 negative real zero, which coincides. So now, we know for a fact that we will have a real zero that is negative. From here, you can do your P's and your Q's, your synthetic substitution, your rational zero theorem, and find your factored form. However, I just wanted to introduce the Descartes rule so you knew it. All right, so this is that first half of the video, and look at we're almost already up to 30 minutes, which is why I decided to do it into 2 separate videos. Please, please, please make sure you're coming to our virtual class or asking questions so I can help you. This is a concept that takes constant reinforcement, and if you don't ask for help, you will get lost. So please take the time to come to class, ask questions, shoot me an email. I'm here to help you. Have a wonderful day.